Do aliens exist? It is one of the most profound questions we can ask about our place in the universe. If you ask the average person, they will probably tell you that life must be out there somewhere. The universe is simply too big, too ancient, and too diverse for us to be the only living creatures. But believing life exists is very different from proving it. For a long time, the biggest problem in astrobiology was knowing where to look. The cosmos is filled with billions of galaxies, each housing hundreds of billions of stars, and finding a needle in a cosmic haystack felt almost impossible. We spent decades listening to the radio silence of deep space, hoping for a whisper that never came. For centuries, humanity lived under the assumption that our world was the center of everything, or at least a highly unique sanctuary in a dead cosmos. Every time we looked at the sky, we saw points of light but no concrete evidence of other shores. Discovering exoplanets in the late 20th century was the first step in dismantling this. Isolation, showing us that planets are common. But finding a world that is not just a planet but a habitable one remained the ultimate boundary. We needed a system that was close enough to study in detail, yet rich enough in rocky candidates to increase our chances of success. That was the case until astronomers found the TRAPPIST-1 system. If you wanted to design the perfect laboratory to search for extraterrestrial life, you could not do much better than this. We already know that rocky planets like Earth are capable of supporting life because we are standing on one right now. So when scientists discovered a nearby star system packed with 7 rocky Earth-sized planets, the scientific community stopped in its tracks. TRAPPIST-1 is relatively close, sitting just 40 light-years away in the constellation of Aquarius. It is a compact, crowded family of worlds that could hold the key to our greatest question. For the first time in history, we had a concrete target, a place where we could focus our telescopes and actually search for signs of biology. Now researchers have pointed humanity's most powerful space observatory, the James Webb Space Telescope, directly at these 7 worlds. They want to strip away the mystery and see what is actually happening on their surfaces. The wait is over. The data is coming in, and the results are rewriting what we know about planetary habitability. Has the Webb telescope confirmed that the TRAPPIST-1 planets can support life, or are we looking at a collection of dead, airless rocks? It is time to look at the data, planet by planet, and see where the search for life stands today. Subscribe to Deep Space Signal. Let's decode the universe together. To understand the planets of TRAPPIST-1, we have to start at the center. The conditions on any planet are dictated by the star it orbits. And TRAPPIST-1 is a very strange host. It is an ultra-cool red dwarf star. Physically, it is barely larger than the planet Jupiter, but it is vastly more massive. Red dwarfs are the most common type of star in our galaxy. In fact, if you look at the 60 stars closest to Earth, 50 of them are red dwarfs, including our nearest stellar neighbor, Proxima Centauri. Because these stars are small and cool, they burn their nuclear fuel incredibly slowly. This gives them a lifespan that is hard to comprehend. While our sun will live for about 10 billion years, red dwarfs can survive for trillions of years. That is far longer than the current age of the universe. In a distant future where all other stars have died, red dwarfs will still be shining, lighting up an otherwise dark cosmos. Observing these stars from Earth is incredibly difficult because their light is emitted almost entirely in the near-infrared spectrum, which is invisible to human eyes and easily absorbed by water vapor in Earth's own atmosphere. But this cool nature is also what makes them fascinating. Because their energy output is low, their habitable zone, the region where temperatures allow liquid water to exist, is extremely close to the star. This means any planet orbiting in this zone is likely tidally locked. Just like our moon is locked to Earth, these planets always show the same face to their star. One side is baked in perpetual daylight, while the other side is frozen in eternal night. This temperature difference is a major threat to habitability. On the dark side, temperatures can drop so low that the gases in the atmosphere simply freeze onto the surface. This process can act as a giant cold trap, eventually draining the planet of its air and water. Furthermore, most red dwarfs are flare stars. They're prone to sudden, violent outbursts of electromagnetic radiation and charged particles that can increase their brightness in minutes. These stellar flares are capable of stripping away a planet's atmosphere and sterilizing its surface. However, TRAPPIST 1 has a surprising saving grace. While it is a red dwarf, observation shows it is far quieter than its cousins. It releases about 30 times fewer flares than a typical active red dwarf. This quiet behavior gives scientists hope that the planets orbiting TRAPPIST 1 might have been able to hold onto their atmospheres over billions of years, keeping the dream of life alive. Although the star TRAPPIST 1 was first catalogued in 1999, its incredible planetary system remained hidden in the dark for nearly 2 decades. The breakthrough finally came in 2017, thanks to a specialized project designed to look for planets around the smallest stars in the solar neighborhood. This was the TRAPPIST telescope project, short for the Transiting Planets and Planetesimal Small Telescope. The project operates 2 robotic observatories: TRAPPIST South, nestled high in the desert mountains of Chile at the La Silla Observatory, and TRAPPIST North, situated in the Atlas Mountains of Morocco. Together, they kept a constant watch on the dim red dwarf. To find the planets, these telescopes used a technique known as transit photometry. The concept is simple but incredibly difficult to execute. When a planet's orbit aligns perfectly with our line of sight, it will pass directly between Earth and its host star. During this transit, the planet blocks a tiny fraction of the star's light. By measuring the brightness of the star over time, telescopes can detect these periodic dips in light. The deeper the dip, the larger the planet. The frequency of the dips tells us how long the planet takes to orbit its star. Ground-based astronomers must filter out Earth's moving air, dust, and weather to measure these microscopic changes, which is like trying to spot a firefly passing in front of a distant searchlight. Initially, the ground-based observations only revealed 3 planets orbiting TRAPPIST 1, but astronomers wanted a clearer picture, so they enlisted the help of NASA's Spitzer Space Telescope. Spitzer, operating in the infrared spectrum from orbit, observed the star continuously for weeks. Spitzer was uniquely suited for this because it was cooled by liquid helium to near absolute zero, allowing its sensitive detectors to pick up faint infrared signals without being blinded by its own heat. The space telescope's data was far cleaner, free from the interference of Earth's atmosphere. When the analysis was complete, the results shocked the world. There were not just 3 planets, but 7. And even more surprisingly, the data confirmed that all 7 worlds are rocky, terrestrial planets of roughly the same size and mass as Earth. It remains the most compact collection of Earth-like worlds ever discovered around a single star, prompting a massive wave of scientific curiosity. The layout of the TRAPPIST 1 system is incredibly compact. To put it in perspective, all 7 planets orbit extremely close to their star. The outermost planet, TRAPPIST 1 hour, is only 9 million kilometers away from its host. In our own solar system, Mercury orbits our Sun at a whopping 58 million kilometers. This means the entire TRAPPIST 1 system could fit easily inside the orbit of Mercury. Because they are so close together, the planets orbit their star at blistering speeds. Let's look at the first 2 planets, TRAPPIST 1b and TRAPPIST 1c. These are the inner hot zone worlds. TRAPPIST 1b is the closest planet to the star. A single year here lasts just 36 hours. The planet is slightly larger than Earth, and its gravity is about 80% of ours, making it physically similar to Venus. Because it orbits only 1.7 million kilometers from its star, scientists originally suspected it might have a thick, Venus-like atmosphere of carbon dioxide that trapped immense heat. However, the James Webb Space Telescope recently checked this theory. By measuring the infrared light emitted by the planet during a secondary eclipse, when the planet passes behind the star, Webb revealed that the dayside surface temperature reaches a scorching 227 degrees Celsius. This temperature matches what you would expect from a bare, airless rock. The telescope found no evidence of an atmosphere. TRAPPIST 1b is a dead world constantly sandblasted by the star's radiation. To measure this, Webb used its mid-infrared instrument, or MIRI, to record the heat coming from the planet right before it disappeared behind the star. Since an atmosphere would distribute heat to the dark side, The day side should have been cooler if air existed, but MIRI saw the maximum possible heat, showing that the day side absorbs all the star's energy and radiates it back immediately, moving outward. TRAPPIST 1C orbits at 2.4 million kilometers, completing a year in 58 hours. It receives about twice as much energy from its star as Earth does from the Sun. Webb's thermal measurements of TRAPPIST 1C showed a similar disappointing result. The planet's surface is too cold to support a thick heat redistributing atmosphere. If it has any air at all, it is either completely airless or has a carbon dioxide atmosphere thinner than that of Mars with no clouds. It appears TRAPPIST 1C formed with very little water. Without water vapor to help create a greenhouse effect, it remains a dry, barren desert. The first two candidates on our list are nothing more than scorched, silent stones, proving that proximity to a red dwarf can be fatal to a planet's air. How can we study the atmosphere of a planet that is 40 light years away? We cannot send a probe there. With current technology, such a trip would take hundreds of thousands of years. Instead, we have to decipher the message hidden in the light itself. To do this, a dedicated team of scientists called the DREAMS team, which stands for Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, secured guaranteed observation time on the James Webb Space Telescope. They focused Webb's state-of-the-art instruments on TRAPPIST, one using a method called transmission spectroscopy. As a planet transits in front of its star, the star's light passes through the thin shell of gas that makes up the planet's atmosphere. The atoms and molecules in that gas absorb very specific wavelengths of light. Different chemical bonds absorb energy in different ways. For example, carbon-oxygen double bonds in carbon dioxide absorb a different wavelength than carbon-hydrogen bonds in methane. By breaking the star's light down into a detailed spectrum, the telescope's near-infrared spectrograph, or NIRSpec, can measure exactly which wavelengths are missing. If certain wavelengths are absorbed during a transit, it leaves a dark line in the spectrum, a barcode that proves an atmosphere exists and tells us exactly which gases are present. However, this process is plagued by a major challenge: stellar activity. Red dwarfs are covered in giant star spots, dark, cool areas similar to sunspots on our sun. When a planet transits, it can cross over these star spots, or the spots can simply alter the overall light of the star. Because star spots are cool, they contain water vapor and other molecules that mimic the signature of a planetary atmosphere. Astronomers must use complex mathematical models to separate this stellar contamination from the actual signal of the exoplanet's sky, ensuring they aren't being fooled by the star itself. Analyzing these atmospheres is easier around TRAPPIST-1 than around almost any other star system we know of. The reason is counterintuitive. It is because the star is small and dim. If a small Earth-sized planet passes in front of a giant bright star like our Sun, it blocks only a tiny fraction of a percent of the light, making it very hard to measure. But when the same planet transits a small red dwarf, it blocks a much larger relative percentage of the star's light. This makes the signal much stronger and easier to detect. The data we get from TRAPPIST-1 is 10 times more sensitive than the data from any other exoplanet system, turning the search for atmospheres into a highly precise scientific game. The third planet from the star, TRAPPIST-1d, sits in a very interesting position. Orbiting just 1 million kilometers further out than Planet C, a year on this world lasts only 97 hours. TRAPPIST-1d is smaller and lighter than Earth, with a mass and size about 30% of our planet. This gives it a surface gravity similar to Mars, just under half of Earth's gravity. Crucially, TRAPPIST-1d lies on the inner edge of the habitable zone. It receives only about 4% more energy from its star than Earth receives from the Sun. So far, the James Webb Space Telescope has not detected any clear signatures of water, methane, or carbon dioxide on TRAPPIST-1d. This seems to rule out a standard Earth-like atmosphere. But it does not mean the planet is dead. Scientists believe the planet could have a thick, volatile envelope, such as a massive global ocean, hidden beneath an obscuring cloud deck that blocks the telescope's spectrometers. If the atmosphere is thin or non-existent, the planet's tidal locking would create a harsh division. The side facing the star would be scorched, while the dark side would be frozen solid. Life would only be possible along the narrow twilight strip between day and night. In this twilight zone, the Terminator line dynamic atmospheric conditions would emerge. Since the day side is continuously heated, hot air would rise and rush toward the freezing night side, creating violent, permanent winds. If these winds are too strong, they could strip moisture away from the surface, dumping it as ice on the night side and leaving the twilight zone dry. However, if TRAPPIST 1D has a thick atmosphere or a deep ocean, it could circulate heat around the planet, keeping temperatures stable on both sides. Some climate models suggest that TRAPPIST 1D could be a water world, holding over 250 times the amount of water found in Earth's oceans. Other studies suggest its atmosphere could be thick and toxic like Venus. The Webb telescope has not yet been able to rule out either possibility. The boundary between a habitable ocean world and a dry, dead desert remains blurred on TRAPPIST 1D, leaving it as one of the system's most intriguing mysteries. As the telescope continues to gather data, astronomers hope to pierce the veil of this borderline world and find out if it is truly wet or just another barren rock. If we look at the outer planets of the TRAPPIST-1 system, we find worlds that are still within the boundaries of the habitable zone, but they are getting much colder. Let's bypass planet E for a moment and look at the outer trio. Planets F, G, and H. TRAPPIST 1F orbits at 5.8 million kilometers from the star. A year here takes about 9 days, or 220 hours. Its physical size is very close to Earth's, but it is much less dense. This low density suggests the planet is composed of about 20% water. However, because of its location, this water would not form calm oceans like ours. Instead, the heat from the star would create a massive greenhouse effect, keeping the water in a superheated gaseous state. This is what astronomers call a steam world. The surface temperatures would likely reach hundreds of degrees Celsius under crushing atmospheric pressure. It would be no more habitable than the gas giants of our own solar system, with thick steam layers blocking any life from reaching the rocky surface. Further out is TRAPPIST-1G, which is slightly larger than Earth. It orbits at 7 million kilometers, taking 12 days to complete one trip around its star. While we know very little about its atmosphere, scientists have detected signs of water here as well. Because it sits on the very outer edge of the habitable zone, it remains a candidate for life, though it would likely be a very cold world, covered in glaciers and sheets of solid ice. Its higher mass compared to Earth might help it retain its volatile elements, preventing them from escaping into the void. Finally, at the outer edge of the system sits TRAPPIST, 1 hour. Orbiting at 9.3 million kilometers, its year lasts 19 days. It is the smallest and least dense planet in the system, with gravity comparable to our moon. Because it is so far from its cool host star, TRAPPIST, 1 hour is likely a frozen ice world, a silent sphere of rock and water ice. With such a weak gravitational pull, it would have difficulty holding on to a secondary atmosphere over time. It could theoretically host liquid water if it possessed a thick, hydrogen-rich atmosphere to act as a powerful greenhouse. But for now, it remains a silent, icy mystery at the edge of the system, waiting for future observations to reveal its secrets. Now, we must return to the planet we skipped. Sitting right in the sweet spot of the system's habitable zone is TRAPPIST, 1E. If there is a true twin of Earth in the entire system, and perhaps in our entire stellar neighborhood, this is it. TRAPPIST 1E orbits its star at a distance that places it squarely in the middle of the Goldilocks zone. It receives about 2/3 of the solar energy that Earth receives from our sun. This means the planet's average temperature could be very close to Earth's, allowing liquid water to exist on its surface without vaporizing or freezing instantly. It is the only planet in the system that sits in this perfect energetic balance. In the study of life, liquid water is the ultimate holy grail. It is the universal solvent, the medium that allows organic molecules to meet, interact, and form the complex structures of biology. Without liquid water, life as we know it cannot exist. And on TRAPPIST 1e, the thermal conditions are just right to keep water in its liquid state on the surface, making it a prime target for exobiology. Physically, TRAPPIST 1e is about 90% the size of Earth. It shares almost the same density and composition, which means its surface gravity is nearly identical to what we feel on Earth. If you stood on TRAPPIST 1e, you would hardly feel a difference in your weight. It is this combination of size, gravity, and temperature that has made scientists obsessed with this world. In the hunt for alien life, this is our golden target. The DREAMS team was so intrigued by TRAPPIST 1e that they decided to spend almost all of their guaranteed James Webb Space Telescope observation time focusing on this single world, bypassing the others to solve its secrets. So far, Webb has observed 4 transits of TRAPPIST 1e. Every time the planet passed in front of its star, the Space Telescope watched, gathering data on the light filtering through its sky. The search for an atmosphere on TRAPPIST 1e is the most detailed exoplanet study in history. The stakes could not be higher. If Webb confirms a stable, life-supporting atmosphere on this world, it will be one of the greatest scientific discoveries of all time, proving that Earth is not unique. The initial findings have already started to come in, and they have given researchers plenty of reasons to keep looking, revealing that the planet's sky is far more complex than we ever imagined. What did the James Webb Space Telescope find when it analyzed TRAPPIST 1e? The first step in scientific discovery is often ruling out what is not there, stripping away our assumptions to find the truth. In the case of TRAPPIST 1e, we can start by discounting several types of atmospheres. First, the data confirms that TRAPPIST 1e does not have a primordial atmosphere. A primordial atmosphere is the envelope of gas a planet is born with, usually dominated by light gases like hydrogen and helium left over from the nebula that form the system. These light gases are easily stripped away by stellar radiation, especially during the chaotic and energetic early life of a red dwarf. This process of photoevaporation and hydrodynamic escape essentially boils off the hydrogen and helium into the void. The Webb telescope found no signs of these elements, meaning they were blown into space billions of years ago, acting like a cosmic leaf blower cleaning the planet's sky. Second, Webb's readings ruled out a super-dense, CO2-dominated atmosphere like the one on Venus. Third, the data also shows that a thin, sparse CO2 atmosphere like the one on Mars is highly unlikely. Believe it or not, all of this is actually good news. Neither a Venus-like greenhouse furnace nor a Mars-like freeze would be good candidates to support life. By ruling out these extreme scenarios, the data points towards something much more exciting. If TRAPPIST 1e had no atmosphere at all, it would be a cold, dead rock. But the readings suggest that it has managed to keep some gas. With primordial and toxic CO2 atmospheres out of the way, the focus turns to secondary atmospheres. These are created later in a planet's life by volcanic outgassing, dominated by heavier molecules like nitrogen, and can support a stable greenhouse effect. The stage is set for a sky that could be very similar to our own, holding the volatile elements necessary for organic chemistry to flourish. If TRAPPIST 1e has a secondary atmosphere, what does it look like? One exciting possibility is a nitrogen-rich sky with a surface pressure of about 1 bar, similar to Earth. Such an atmosphere could transfer heat to the frozen night side, allowing a global liquid ocean to exist despite the planet being tidally locked. However, the latest atmospheric models suggest a different fascinating scenario. Our sun has a surface temperature of 5,500 degrees Celsius, but the red dwarf TRAPPIST 1 is much cooler, at just 2,300 degrees. Because of this lower temperature, most of its energy is emitted in the near-infrared spectrum. If TRAPPIST 1e has high levels of methane in its atmosphere, a strange phenomenon occurs. A reverse greenhouse effect, methane molecules absorb infrared energy high in the atmosphere before it can reach the surface, re-emitting it back into space. This actually cools the planet's surface. For a tidally locked world, this means a global ocean is unlikely. Instead, liquid water would only exist on the permanent day side directly facing the star, creating a localized warm zone. If photosynthetic organisms exist on this day side, they would have to adapt to the star's unique light. On Earth, plants use green chlorophyll to absorb blue and red sunlight, but on TRAPPIST 1e, where the light is almost entirely infrared, organisms might need black or dark red pigments to capture every available photon of this lower energy light, creating a bizarre dark ecosystem under a giant red sun. But this is not bad news for life. In fact, a localized warm region on the day side is the perfect environment for Darwin's warm, little pond hypothesis. The idea that life began in shallow, chemically rich pools of water where organic molecules could concentrate and react. Alternatively, if water is scarce or locked as ice on the dark side, the planet could experience Terminator habitability. In this scenario, the day side is too dry and the night side is too cold, leaving only a narrow, circular band of permanent twilight as a habitable zone. Here, in the eternal sunset, temperatures would be moderate enough for water to pool and life to find a stable home. This boundary zone would be a dynamic region, where winds carry heat back and forth, creating a planetary ring of life. What would it be like to stand on the surface of TRAPPIST 1e? If you looked up, the red dwarf star would appear 4 times larger in the sky than our sun does from Earth. The landscape would be bathed in a deep red-orange light, creating the impression of a sunset that never ends. But this beautiful scene hides a deadly reality. Red dwarfs are notoriously volatile. Even though TRAPPIST 1 is quieter than most, it still releases massive solar flares. The worst solar storm ever recorded on Earth was the Carrington event in 1859, which shut down telegraph systems. TRAPPIST 1 releases a flare of this magnitude once every 2 days. To survive this bombardment, TRAPPIST 1e needs a shield. Without a strong magnetic field, its atmosphere would have been forced into space long ago by the relentless solar wind. Fortunately, the planet's close orbit might be the very thing that saves it. Because its orbit is slightly eccentric, the gravitational pull on TRAPPIST 1e changes as it moves closer to and further from the star. This gravitational tug-of-war stretches and squashes the planet's shape, creating internal friction. This process, known as tidal heating, generates 24 times more internal heat than Earth experiences. We see a similar effect in our own solar system with Io, Jupiter's volcanically active moon, which is kept molten by the gravity of Jupiter and its sister moons. This immense tidal energy also drives active tectonics, constantly recycling carbon and other gases through the planet's interior. This volcanic cycling is crucial for maintaining a secondary atmosphere, replenishing what is lost to space and stabilizing the climate over long timescales. On TRAPPIST 1e, this constant flexing keeps the planet's core active and molten. A churning core of liquid metal is the engine that drives a planet's magnetic field through the dynamo effect. If TRAPPIST 1e has a strong magnetosphere powered by this gravitational engine, it could easily deflect the stream of charged particles from the star's flares, protecting its atmosphere and allowing life to develop in safety. The very gravity that threatens to rip the planet apart might be the key to its survival, turning a hostile relationship into a protective shield. Where does the search for life in the TRAPPIST 1 system leave us? We are looking at one of the most exciting frontiers in modern astronomy. We have an Earth-sized rocky planet with active geology, a potential magnetic shield, and a location that could support liquid water. It is a world where all the ingredients for life could be present. Yet, it could also be a cold, dead sphere of rock. The truth is that we do not know for sure. Not yet. This uncertainty brings us face to face with the Fermi paradox. If planets like TRAPPIST 1e are common and have all the conditions for life, why does the universe seem so silent? Are the active youth of red dwarf stars a filter that destroys atmospheres before life can start? Or is the galaxy teeming with simple, silent organisms that do not build radio transmitters? Discovering the truth about 1E will help us answer this paradox, telling us if Earth is an anomaly or part of a crowded cosmic community. But astronomers are not giving up hope. Webb's initial observations have taught us a great deal, and scientists are refining their observation techniques to extract even cleaner data from future transits. They want to confirm the presence of secondary gases like carbon dioxide and nitrogen, bringing us closer to a definitive answer. For the final word, we might have to wait for the next generation of space telescopes, like the proposed Habitable Worlds Observatory. Scheduled to launch in 2041, this observatory will be specifically designed to search for signs of life on planets around stars like our own, using advanced coronagraphs to block starlight and image exoplanets directly, searching for the telltale atmospheric signatures of oxygen and ozone. Until then, the fact that we can even ask these questions is a testament to human ingenuity. We are measuring the microscopic absorption of light passing through the atmosphere of a planet, 40 light-years away, using a giant gold mirror floating in the cold vacuum of space. It is an extraordinary technological feat. And as we continue to look, the discovery of life beyond our solar system feels more and more like an inevitability. We have found the worlds, we have built the telescopes, and we are decoding the signals. The only remaining question is not if we will find life, but when.